Okay, for section 5.2, we're going to be working with some similar ideas to what we just did yesterday in 5.1. One of the big differences, though, is going to be we're ultimately going to be given an equation, okay, instead of an expression. Okay, yesterday we had an expression and we were just told to simplify it, okay, or write it in some particular form. Okay, what we're going to try to do today is we're going to take an equation that we're given and we're going to try to prove that this is an identity. Okay? Remember we talked about yesterday with identities is that if this is an identity, that no matter what I put in here for x, okay, this sentence is going to be true. So if I told you to put a 5 in here, and you put a 5 in all those x spots, and you do the math on it, it had better equal what? Better equal 2. All right, and we could show that with 5. We could show that with 10. We could show that with -6. Okay? We could pick as many examples as we wanted to prove that this is true. But ultimately, how many examples would convince us that this is a true sentence? Okay, just one would do it for you? Okay, well if you tried one and it worked, you'd have reason to believe that it might be true. Agreed? Okay, but are you convinced that it's going to be true for every x? I mean, if you tried 5 or 6 of them and they all worked, then would you be convinced? Okay, but would that necessarily convince your neighbor? Maybe. Okay. Ultimately, though, if we wanted to prove this is true, okay, how many of the examples would we have to show? All of them. Okay, we'd have to show every single number. All whole numbers, fractions, decimals, negatives, positives, etc. Okay, we'd have to show every one. So is it possible to prove it by example then? No. And hence we won't. Okay, instead we're going to prove it with algebra. Okay, so the general strategy, we're going to look at some of these general strategies in a minute, okay, is to transform either one or both sides, okay, so that we have an equality. Okay, now 2 really can't do much simplifying that. It's 2. Okay, so in this particular case, we're going to focus on the more complicated side, which is this. Now, we learned yesterday that if we have a situation like this where we have a subtraction, and then we can add these two together, okay, or subtract, whatever the case may be. So I'm going to go ahead and do that same thing I did yesterday. I'm going to get a common denominator. Okay, and we'll see how this looks. And this is what our work is going to look like for our proving identities today. So we're going to have times x plus 1, and then here we're going to have squared minus 1 times x minus 1. Okay. So we're going to go ahead and get a common denominator. Okay, and then we're going to put those together. We're going to have the same denominator. We're going to have x minus 1, x plus 1. And then in the top, I'm going to go ahead and multiply this stuff out here. So we have two FOIL problems on the top that we need to deal with. So we're going to have x cubed plus x squared minus x minus 2. So it's going to be one of our parentheses, minus 1, I should say, not minus 2. Thank you. So we have that. And then we're going to be minus. And then if we FOIL these two out, we're going to have x cubed minus x squared minus x plus 1 this time. Okay. And then ultimately, if we combine like terms, we're going to have x cubed minus x cubed. Those are going to be gone. X squared minus negative x squared is going to be plus, so it's going to be 2x squared. We have negative x minus negative x, which is going to be gone. We have negative 1 minus 1, which is going to be minus 2. All right, questions so far? Now, that still doesn't look like 2, does it? Looks simpler than what we started with, but it still doesn't look like 2. So what we want to recognize is that that top has a factor of 2 in common. So if we factor that out, and I want you to also notice that look at what we have on the bottom here. If I were to square that, or not square but FOIL it, wouldn't I also get x squared minus 1 on the bottom if I were to multiply the bottom out? And ultimately what happens? Those cancel out and I get 2 equals 2, don't I? Okay. So that is the algebraic method that we're going to use to prove some such equation as this is an identity. Okay, like I said, that doesn't look anything like 2, but it is, isn't it? Okay, if we algebraically simplify it, okay, it simplifies to 2. So no matter what x is, okay, you can pick any x you want to. If you plug it into this expression, you're going to get 2. Fair enough? Okay. So with that said, let's take a look at these general strategies that we're going to use here. Okay, this is the first one. I'm on page 455 if you want to follow along here. So general strategies for proving an identity are as follows. We're going to start with number 1 here. The proof begins with the expression on one side of the identity. Okay. and the proof ends with the expression on the other side of the identity. That's exactly what we just did in that example. We took one side of the identity and we transformed it into the other side. Okay, so that's exactly what we just did, those two steps right there for that one. Okay, and then the proof in between consists of showing a sequence of expressions, each one easily seen to be equivalent to its preceding expression. Okay, so keep in mind, going back to my previous problem, if I just did that and I had that, okay, is that going to be good enough to prove it? I mean, anybody can just write that down and then write 2 equals 2. Yeah, sure. Okay, how so? Okay, my steps, okay, are the answer to this question. Okay, each step that I did, okay, and when we do this, let's all do this exactly the same in a vertical manner like this. Okay, not strewn left to right and all over the place. So one step at a time, go vertical and tell me, show me what you got each time that you did something. Okay, I should be able to, even though I know a lot of math, if there's people that don't know a lot of math, they should still be able to follow what you did. Make sense? So don't skip from this step to this step, okay, and lose all this intermediate work. Okay, if you're going to prove this, we need to see, okay, how you got from each step one to the next. Fair enough? So that's ultimately the general strategy. Okay, that's general strategy number 1. Okay. So, here's number 2. And this is ultimately kind of the same thing we just said here, but this I mentioned this earlier, the more complicated expression. Pretty obvious which one was more complicated than the one we started with today, right? So if we start with the more complicated expression and we would work towards the less complicated one, that's generally a pretty good way to go about it. Okay. Number 2, if no other move suggests itself, convert the entire expression to one involving sines and cosines. Okay, we're gonna spend most of our time on identities that have to do with trig functions. Okay, so this right here, I'm going to put a circle around it, very important. Okay, if nothing else seems to be reasonable, if you don't see any other identities that might work to transform anything or any fractions to put together, etc., okay, then one step that's usually worthwhile is to change things in terms of sine and cosine. So if you have any tangents, secants, cosecants, cotangents, change them to their cosine and sine equivalents. So in other words, replace tangent x with sine x over cosine x. Something like that. Okay, that might do you some good. Okay. Number 3, we've been working with here for the past couple days a lot. Combine fractions into by combining them over a common denominator. So if you have 2 different fractions, okay, get a common denominator and add them together. Okay, those are things that we want to look for. Remember I talked about earlier. Okay, to get good at this, we need to start recognizing patterns. Okay, these are a couple of patterns that come up a lot. Okay. Can we do this? Can we do this? Try this, try that. Now, everything you try when you do this, is it always going to work? No, not necessarily. Okay, but ultimately, you want to try it. If it doesn't work, then go back and try something else, okay, until you figure it out. Like I said, it's kind of like a puzzle.
For that step number 2,
yep.
When you change everything to sine and cosine, if it doesn't all cancel out, you have to change it back?
Not necessarily. I mean, it kind of depends. I mean, it might not all cancel out, but you might be able to do something with it once you put it in that form. Okay. We'll see some examples in a minute, though. Okay, let's take a look at this identity right here. Actually, there's one I want to do first. Sorry. Page 455. I want to look at this one. Tangent x plus cotangent x equals secant x cosecant x. Okay. Now, we might look at that and say, okay, well, if I'm going to transform the more complicated side into the not as complicated side, I'd probably look at that and say, don't they look kind of equally complicated? Okay. So the other thing that you can do, you don't have to, but you can do it, is you can work with both sides. Okay, transform both sides until you get an equality. That's fine too. Okay, let's go ahead and do it the first way though. Let's try to do something with the left side, let's say, and see if we can get it to look like the right side. So if I have tangent plus cotangent, we know that adding those doesn't do us any good. If it was times, it would obviously be 1, but it's not times, it's plus. So I would use strategy number 2 then, which is to change things in terms of sine and cosine. So if I go sine x over cosine x plus cosine x over sine x, okay, that would be a valid step. And at that point, we have the fraction. Okay, so if we have a fraction situation, what do we generally want to do with 2 fractions? Add them up, get a common denominator. So cosine x Sine x is going to be our common denominator. And we're going to have sine squared x on top here. Then we'd have cosine squared x on top. And conveniently, what's going to happen when we add those two numerators together? What's sine squared plus cosine squared equals what? 1. Okay. And what do we know about this? If I have 1 over cosine times sine, isn't that the same as secant cosecant? And what were we trying to show this equaled? Secant cosecant. So that worked out nicely, didn't it? And all we did is those two steps. We changed things to in terms of sine and cosine, and we added the two fractions together. And when we did that with our identities, it worked out, didn't it? Okay. Now, like I said, with working with both, could we have, at the same time we did this side, started working with this, could we have changed this to 1 over sine times cosine? And then just been done with an inequality here, having it equaled 1 over cosine sine? Sure. As long as you show both sides are equal, okay, you can either work with one side and show it equals the other, or you can work with both sides until you get an equality. Fair enough? Alright, now let's look at this one right here. We're trying to prove that, that these two are equal to each other. Sine x over 1 minus cosine x equals 1 over cosine x, 1 plus cosine x over sine x. Now this doesn't lend itself into our changing to sine and cosine because it already is sine and cosine, isn't it? Okay. Now there's one thing that you have to be real careful with on this problem. Okay. And what you have to be careful with is the following. You cannot use the cross product property here. Okay. People generally try to say, oh, okay, well then I can go this times this equals this times this. Nope, can't do that. Okay, because in order to use the cross product property, you have to already know that these two are equal to each other. Okay, the cross product property says that if A over B equals C over D, then AD equals CB. Okay, so the if part is the important part. So if these two are equal, then you can do that. But okay, what are we trying to? We're trying to prove that they're equal. Do we know they're equal already? No. So you can't use the cross product property. So do not use cross product. Okay. If you do, that's not a valid form of proof here because you're assuming already that they're equal by using that. Okay. So what do we do instead? Well, in this case, it's we got to think about how we're going to get this to be transformed into that essentially. And what you want to recognize is that if I have 1 minus cosine x, what would be the conjugate of 1 minus cosine x? 1 plus cosine x, correct? And so on the left-hand side, is it okay for me to multiply both the top and the bottom by 1 plus cosine x? Working with the left-hand side here. Okay, remember, because this is just what? It's 1, so I'm not changing anything, I'm just changing the form. So if I do that, I'm going to have sine x, 1 plus cosine x. And then on the bottom, okay, I'm going to have 1 plus, nope, I lied, 1 minus cosine squared x if I multiply that out. Now, on purpose, I didn't multiply the top out. I left that as is. See why in a minute. Okay. All right. So if I multiply those two together, okay, what I want to recognize here is what is 1 minus cosine squared x? Okay. Isn't it sine squared x? My Pythagorean identity tells me that sine squared plus cosine squared is 1, so therefore 1 minus either of them is the other. Okay, and what does that do for me? Sine x and sine squared x now can cancel out. We're going to wind up with 1 plus cosine x on top, sine x on the bottom. And does that equal what we set out to have it equal? Sure. Okay. Now in this particular case, if you did do the cross product, okay, you would get an equality. Okay. But again, the cross product property is not valid here because that would be assuming that these are already equal. We're trying to prove that they're equal, not that they already are, and that we can, get an equality by doing the cross product. Okay, so that's going to be a strategy here. That's another strategy we can use. You can add that to the list. Okay, if we can't think of anything else, how about multiplying by the conjugate? Will multiplying by the conjugate do anything good for us? In this case, it did. Okay, will it always? No. Okay, but in this case, it did. So just another trick in our bag of tricks to use to be able to handle these problems. Now, let's look at, there's a general strategies 3 on here, just a couple more other ideas that you can use. Okay, the first one on this group is that we need to use an algebraic identity like the difference of two perfect squares. We've done that quite a bit today, haven't we? Okay, so again, just another pattern that we can try to use. Okay, all right, and then ultimately number 2 is always be mindful of the target expression and favor manipulations that bring you closer to your goal. Okay, think about what are you trying to transform your expression into. Okay, always try to do things that are going to bring you closer to what you want on the other side of the equation. Okay, so if you start doing a bunch of stuff on the left-hand side that doesn't look anything like what the right-hand side looks like, okay, you might be going the wrong way. True? So always try to think of things that you can do, okay, that will get you from expression A to expression B. Okay, page 457. Yeah, next. We'll finish up with this one. We have cotangent squared u 1 plus cosecant u equals cosecant squared u minus 1 plus cosecant u. Alright. Now, in this particular case, okay, we always, and this really should say in any case, we always have a choice. We can either manipulate one side or both sides, or either one. It doesn't matter if we do left, right, or both. Okay, what I would recognize here is that you have cosecant squared minus 1. Okay, you could change things in terms of sine and cosine here, but it turns out in this case that if you just check this out being the difference of perfect squares, what's going to happen there? Okay, won't that and that be gone? Okay, and so on this side we'd have cosecant u minus 1 over here. True? Okay, we also know, okay, that on this side, cotangent squared, we remember yesterday we learned that 1 plus cotangent squared is equal to cosecant squared. True. So wouldn't cosecant squared u minus 1, and then 1 plus cosecant u on the bottom, and then if we do the difference of squares on the top again, we'd have cosecant u minus 1, cosecant u plus 1, all over 1 plus cosecant u, cancel, cancel, and ultimately we'd have cosecant u minus 1 equals cosecant u minus 1. And so in this particular case, what did I do instead of manipulating one side? I manipulated both sides, didn't I? Okay, and just showed that at some point, if we do these reversible steps, that we get down to inequality. Fair enough? So is that better than the other way? No, not necessarily. Sometimes it works out that it's nicer to deal with both sides. Sometimes it's easier to just deal with one side. Okay, our work for today is on your Math Excel.